Roden Schwartz is a leading manufacturer of value instruments designed to help you maximize your bench's performance for everyday applications. They just announced an industry first, complete solutions with all the upgrades up front for one price. Now through December 31st, 2019, save up to $10,000 on Roden Schwartz solution packages that come with fully loaded test and measurement instruments right from the start. When you invest in Roden Schwartz products, you get the highest quality engineering, plus all the bandwidth, channels, inputs, memory interfaces, and signal generation you'll ever need. Learn more about Roden Schwartz value instruments and this limited time promotion at askanengineer.us. That's askanengineer.us. This is the Amp Hour Podcast. Released November 3rd, 2019. Episode 465. An interview with Ted Yapo. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Ted Yapo. I'm this week's guest on the Amp Hour.
You are. That is very self-aware. How you doing, Ted?
I'm doing well. How are you?
I'm good. We're going to be talking about your wide range of projects and the things that you lovingly share online and the fun stuff that you've been working on. But what's your background? How'd you get into all of this electronics-y stuff?
You know, I got into it as a kid. I blame Radio Shack for the whole thing because my parents were, I think they had a credit card there because they would bring home stuff for, books and kits and whatnot. And this was, in the early 80s, through mid 80s. And I just loved that stuff. I couldn't get enough. And so, I think I was soldering at 9 or 10. I remember burning my fingers once, and I haven't done it since.
But, wow.
Yeah.
I have to learn that. I've yet to learn that trick, so I might ask you about that after the show.
Yeah. But that's really how it started. And then it was, it's really been a hobby for most of my life. I studied engineering physics in college, which was basically the core electrical engineering curriculum and the core physics curriculum kind of mashed together. And then, when I got out, recruiters said, well, what is that? I couldn't tell them, so I ended up doing work in image processing at first, software stuff. And they didn't tell me. I was working there for 6 months or so before they told me who the customer was. And it was one of those 3-letter agencies that you hear so much about these days.
Yeah.
And so,
I guess if you're not seeing the actual images, you wouldn't know what it is, right?
Yeah, that's exactly right. And there were a whole bunch of things you needed to do before you could actually see the imagery. And I just didn't like the kind of constraints of that work. You kind of get locked into it at some point. And so I moved around a bit. I did some work in finance. Did some consulting work, and then finally got back into the image stuff, which I really liked, and wrote software for color photocopiers and color fax machines, which never caught on in the States, but they were big in Japan at one point. People would fax, family snapshots and stuff, and that work was all in assembly because that was back in the day where it made much more sense to to save a few cents on every part because you're going to sell 1 million of them and just, spend $50,000 on NRE to have an engineer write everything in assembly.
Right.
Those were custom processors too. They were custom.
Oh yeah. I was going to ask what processor was on.
Yeah, it was a custom parallel processor. Because image processing is it's embarrassingly parallel. And so, at some point I graduated to writing the tool chains for that stuff. And this was before parallel stuff was on the desktop. And then, the interesting thing was those skills transferred directly into networking. And so I went to a networking startup where they had built their own parallel processor, and it had 8 cores.
That's like like a threading kind of thing. Like that's what you mean by parallel processing there?
Yeah, exactly. I mean, there were eight cores on the die, and then there were 8 of those on the board. So there's these 64 cores all going at once to try to get networking packets through. And so
Oh, okay.
they hired me as principal engineer. I knew nothing about networking. I mean, a little bit because I'd hooked up some
Yeah.
Linux boxes and stuff.
Sure, sure.
And it turns out that, there's a whole bunch of it that wasn't networking at all. And of course you pick up the rest of it, right? You pick up the context, but this low level coding transferred over directly, which was, worked out pretty well.
Yeah, that's great. And is that like, I mean, I guess right now they still do that, but just on a broader scale. Now it's not 64, it's what, many, many more processors than that or what?
Yeah, I would imagine that they do. I still have some friends that work there, and they do the same kind of thing. It's it's a tough problem. It's the kind of thing where on the leading edge of performance, it makes sense to code things at that low level. It just does. You just can't afford the overhead, even though it's minimal these days of a compiled language. Everything's just kind of hand coded, but you do want the velocity that you get with with software or firmware rather than having everything hard coded.
Yeah.
In an ASIC, because even though that's faster, it's the time to market kills you.
I remember the first, so like, I've done web stuff now for a while, not good, but the Amp Hour has a website and I administer it and other websites and stuff like that. And that's kind of how I learned Linux, honestly, is doing some of the server side things. But I remember like the first time I learned, I'm like, wait, each computer connecting to this box, it's like getting its own like service and thread, and like everything is like happening. And then I started thinking about like video streams, and like every time people are streaming video that's not a broadcast, that means that those are all individual connections. It's like, oh my God, there are a ton of things happening here. There's so much like hidden from the casual web user like I used to be. And then you start digging into it and it just kind of overwhelms you from like a DevOps perspective and like you're saying, the networking perspective of like having individual connections. It's kind of bananas.
Yeah, it really is. And then, at the very bottom of the sort of networking stack, you get all these packets. You don't know what they're attached to. Sometimes you have to keep track of what stream they're attached to. Mostly you try not to, because you just don't have that much time. And so, it's this juggling act of trying to get everything out, in order on time. It can be a real challenge. It's an interesting field.
Yeah, there's a lot of technical expertise there for sure.
Yeah, absolutely. And that doesn't even, touch the routing issues, right? The larger issues of how do you calculate the routes and how do you deal with failure and all those things. Those are at, another level entirely.
So then you said you were doing some you're back into imaging stuff. What did that look like? What did that look like?
Yes. So that was it. So that was the office equipment stuff. And so, it was, again, they wanted to spend, a couple of dollars on a processor. And, there's a lot of data in an image. You think about, you buy these things now and they sell them at a loss, right? These multifunction, peripherals. You buy it's got the scan, print, copy, fax all in one, the inkjet things. Sometimes you can buy the new unit that comes with cartridges for less than a set of replacement cartridges.
That's right.
It's the old razor and blades thing, right? It's ridiculous. And so they don't want to, they want to drive the hardware cost to zero. And so they want to put in the cheapest processor they can and still get good performance, right? They want competitive performance. There's a lot of stuff you need to do to get the raw data from a scanner so that it looks like a photocopy, right? It's one of those, I think it's really the only imaging application where you can directly compare results, right? If I take your picture with my phone and I hold it up, well, that's you in person versus a 2D thing. If I make a photocopy, I have the original and I have the copy, and I can put them right next to each other, right?
Yeah.
And not only can I do that, I can look at them here, right, in this fluorescent lighting. I can take them to the window where the colors are different. It's a very demanding application, and people are picky, especially with color photocopiers. Like, well, that doesn't look right.
Right. Human eyeballs have their own like log scales and like weirdness like that, right?
Absolutely. And inks react differently. Some of the inks fluoresce under fluorescent lights, right? They look different than in natural lighting for a number of reasons, and it's it depends on the paper that people typically throw the cheapest paper they can find in there, and that doesn't work very well. So, adjusting your algorithm to a whole bunch of different parameters that people could throw at it, and you're just constantly tuning and tuning and tuning, and trying to do that at speed, right? Because
Right.
you have to keep up with the scanner, and you have to keep up with the printer, and they don't spend a lot of money on buffering. Now, these days it's easier because memory's cheaper and the processors are cheaper. But in those days it was a real challenge to make everything work at speed.
So then that was the end under the vision type stuff, or still?
Yeah, and then later on I did. I went kind of after the networking startup. We were acquired by Cisco at some point. I stayed there for a little bit, and then after that, did some consulting with a couple of guys that I worked with previously. We just did some consulting in embedded systems, generally. And then I decided I wanted to go back to graduate school. And
cool.
So I did some computer vision stuff there. This was midlife, I was mid-30s or so, and did that for a while. And then, so it was like LiDAR-based computer vision stuff. So LiDAR was just kind of hitting the scene at that point. And it was, it's kind of scene analysis from LiDAR, and not just, the little LiDAR sensors you buy today are just distance sensors, really. I mean, and they're just used as, I just want to measure the distance. I don't want my robot to roll down the stairs or whatever. But these are scanning LiDAR, so you could get an image, a depth image of a scene, and doing analysis in there. One of the papers I did was for finding, and it didn't even actually get published, but this was some of the most interesting work that I thought was finding telephone wires and power wires from LiDAR. Because it turns out they're a tremendous hazard to military pilots, helicopter pilots, and those sort of things. Wires, they're tough to see visually, and they can be a real problem. And so, how do you recognize these things from LiDAR scans? And so that was an interesting problem. And then I also did some kind of transitioned into augmented reality stuff. And so you see AR and VR today, and it's a lot of either image-based, where you're putting things into images, right? Or it's augmented reality, where you're kind of overlaying images onto a scene. But the work I was doing was projector-based. So you'd have
kind
projectors.
of like Jerry's recently completed Kickstarter thingy.
Yeah, it kind of, except you'd use like your normal office projector kind of thing to project onto shapes on a table, or to project onto objects, or project onto those sort of things. So there wasn't you didn't have any equipment that you kind of had to carry with you or have on you, and a whole bunch of people could sort of share the same thing. And we actually did this at room scale. So we had big projection screens that you could move around in a huge space, and project on those to do like for architectural daylighting simulation. So you want to build a space, and you want to sort of be in the space and see how it reacts during the day. And you want to minimize artificial lighting. You want to maximize natural lighting. You want to see how people react to the space that you've created, depending on the time of day, the time of year. You're going to put a conference table in the middle of the room. Well, is this going to be a problem with glare on, in December when the sun is really low?
Oh, yeah. Right.
In this, the way the building is oriented. And so these are kind of things that architects, designers want to explore. And especially when you have a client there, they can't necessarily visualize it in the same, in CAD or in models, as well as they can be just kind of sitting in the room. So the idea was to build, room scale simulators of design spaces.
I mean, it sounds like that's going to be a high-end architecture firm, because that sounds like a high-end piece of equipment as well.
Yeah, it was cobbled together in typical, kind of grad student fashion. Was cobbled together from whatever we could find, right? Projectors that we could have. And
like
and
dumpster finds and stuff like that.
Yeah, and a lot of it was borrowed. I mean, we just couldn't afford to have that stuff, and really didn't have a need, for it full time and long term.
yeah, grad school. I mean, that's interesting too, of like the going back to grad school kind of midway through your career. I mean, was that a tough transition back into the academic life, or was it just more like
You,
working in a lab kind of?
it was at first. It's kind of weird. Well, the mistake I had was, I got to a position in my career where I thought, this is the opportunity I have to do it, just because of the way things worked out with the startup and the situation we were in at home. And I thought, if I'm going to go back to grad school, this is my shot.
Uh-huh.
And the thing I didn't kind of factor in was I had two young kids at home.
Uh-huh.
And
Yeah.
so, the amount of time, and they were 1 and 2 years old. And I thought, oh well, they're 1 and 2 years old. In another
What could they
year or two,
possibly
this
need?
is going to be easy, right? This is the hard part. It's going to be easy when they're 3 and 4 and 5 and 6, and it isn't.
Yeah.
And so that was a real challenge to balance that. I have a lot of respect for people who go through that. It was very difficult. As a grad, I did my master's when I was in my early 20s, and that was kind of a slog,
Yeah.
right? And then but somehow I didn't factor in the other. And then going back, if you've been out of school for 10 years, there's a lot of stuff you forgot.
Like
You know,
like day-to-day knowledge kind of stuff, like just
no, just
fast access memory type stuff.
hardcore. I had to take qualifying exams and like linear algebra, for instance. I took a linear
Oh
algebra
yeah.
class when I was an undergrad, and it was just like the most opaque subject I could imagine. And I was just like, I don't remember any of it. I mean, and I didn't end up using it in my career, in my work. And so it was all gone.
Yeah.
And so, when I said, oh, I need to learn this again, I picked up a book and I'm like, yeah, it's just as opaque as I thought it was. And then I found these online lectures. MIT has these open courseware lectures. I don't know if you've seen
Yeah.
these.
Of
So
course. Yeah. The MITx and yeah. Right.
yeah. And so, I found Gilbert Strang's lectures in his linear algebra course and went through those. I'm like, oh my gosh, this isn't that hard. This makes sense.
Just the book
And,
suck or what?
yeah. The way it's presented is just, I don't know, just from a theoretical point of view, as opposed to this is how this works, and here's why you want this. Here's how it applies. And for me, that's very important. If I can't break it down into how would I use this myself,
Yeah.
the information just evaporates.
Yeah. Yeah. The
from
give a
my
shit
head.
test. Like, why should I give a shit?
Exactly.
Yeah. It's tough too. I mean, like, and I feel like if, I've harped on this on the Amp Hour for years now, but like if they would pull a piece of test equipment into the room when they're showing you the math, it's like, hey, look at this. This was made with an FFT. Now we're going to learn FFTs. Like, oh, okay,
Yeah.
that's cool. Like, I want to know that. That's very relevant to my interest because it's right in front of me. It's just
Yeah, absolutely.
Yeah.
And I think what happens when you don't do that is the folks who don't have that learning style kind of self-select into becoming professors.
That's
so
right.
It perpetuates itself.
I agree. Yeah. Yeah. I'm sure they're very talented as well. Like they are self-selecting, of course, but
Absolutely.
Yeah. The culture, we're really talking about the cultural side of it, right?
Absolutely. Yeah.
Well, that's a fun reintroduction then.
Yeah, that's right.
Yeah. I had a very tiny taste of that when I was convinced by a former coworker that I should get my professional engineering license. And I was like, oh, great. And this is like
wow.
7 years out of school. And then I'm like, oh, I have to go take the fundamentals of engineering exam now. And it's like, just it's a smorgasbord of all engineering knowledge. And I had a real tough time with thermodynamics and the stuff I had a tough time with the first time around. It was I luckily passed, but then I didn't end up using it. So
yeah.
Oh well.
Yeah, I've known people who've gone through that. It's a grueling thing and grueling course. And I guess it's important, right? If you're going to sign off on big projects, you got to know your stuff.
Yes, you do, and I have not signed off on a big project yet, nor have been offered a scenario where that is the case. Right. And that's okay. That's okay. I don't want to anymore. So you did some consulting for yourself, though, right? I mean, I guess that's one space where a PA might be useful, is consulting, stuff like that. What would that look like?
Most recently, well, initially, I had a few partners, and we did some work for folks we had worked for as employees before, and they had plenty of work and were able to hire on consultants. And the consulting work I've done since then on my own, again, has mostly been, with people that I've either worked for or worked with before. It tends to be the kind of easiest way to find clients. And in many cases, it's, my phone rings and it's somebody that needs something. I'm not going out there and hustling and trying to find work.
Right.
Which is great. And I think that's, you hear a lot about, how do you grow your business? But those connections are key, and they lead to, if it's not them, it's somebody they know or somebody that they've worked with in the interim. You just can't beat that kind of network if, once you build it. And the problem is it takes time.
Yeah. I think proximity, even so, like from a social network proximity kind of thing of like, how many hops away is it? How well do they know you? That kind of thing. Like a really strong connection of mine might introduce me to a weaker connection of theirs. But because that strong connection is in between, it's relatively close in terms of that,
right.
in my own experience. And then I think geographic proximity as well, that really helps. If you're near someone, if you can go talk to them in person, even if you don't know them that well, if you can go sit in a room with them, it's like, oh, okay, that's a much more likely scenario to get some work, I think.
Yeah, that's the whiteboard factor, right? If you can get together in front of a whiteboard and try to explain yourself, it's makes everything a lot easier.
But it's a lot better. Yeah,
right.
Yeah. Does that mean that a lot of your clients you're New York based?
I'm New York based. Yeah, mostly I worked in Massachusetts.
Oh, okay.
So not that far away.
Yeah, or New Englandish area.
New Englandish, yeah.
Yeah. That's cool. Yeah, I mean, New York itself has a lot of weird, like East Fishkill. That one always gets me. Like I know some people in that area,
right.
But like, that must have been like some sick tax break because it's near Albany and like that's where the capital of New York is, and like that must be why that's there. But that place never ceases to amaze me. It's like you're in the middle of nowhere. You're near the Catskills, kind of, right? But like,
right.
A beautiful area, but it's like, okay, now we're going to plop a bunch of fabs there. It's okay.
There's a bunch of little pockets, right?
Yeah.
Like that. But yeah, I'm kind of in the middle of nowhere part of New York. So
yeah, that's nice too.
Just north of Albany. Yeah, it is.
It only hurts if you're trying to branch out with the network, but I guess the internet helps that, and that's something that you have done quite a bit lately, and that's kind of what we're talking about here is your projects that you've posted to Hackaday and Twitter and other places. Right. When did that all start?
Probably I know exactly when it started. So the 2016 Hackaday Prize, I don't know how. So somehow I wasn't aware of the prize before. Obviously I knew Hackaday for years, but somehow I didn't get I don't know. I didn't realize that the prize existed. And
well,
I saw it.
If someone helped run it for the early years, that's on me. So sorry about that. Yeah,
that's probably on me because I was busy with other things. But I figured out. Okay. I have a project I can submit to this, and in order to do that, you need to post it on hackaday.io. I'm like, okay, well, I'll make a project on hackaday.io. And I did that. And that was the diode clock. That was the first project I really, really published online.
First of 51 projects that are online, just so people have a relative measure here.
Right. And that took a prize in the first round. So I won $1,000 for that project. And I won another round that year too. And sort of that got me doing it. I was like, this isn't, obviously it's nice to win a little cash, but the thing I realized right away was documenting something for somebody else to read really makes you have to understand it, and you have to kind of go beyond the level that you normally would that I normally would with a project. To document it, you need to like, you can't just say, "Oh, I kind of get what would happen here."
Yeah, right. Yada yada yada.
Right. And I kind of fool myself a lot when I work on my own. Like, oh yeah, I understand how that's supposed to work. I kind of get this. And when you're documenting it for somebody else, you can't really do that.
Yeah, I always think about that with textbooks. When you see the answer to the problem, you're like, "Oh yeah, I would have gotten that answer." It's
right.
Like, well, where's your work, Chris? There's no work here.
Right. Yeah, it's different when you have to do that. And the other thing I realized very quickly was I can search stuff that I put online much easier than I can find stuff in my lab or my office or
Oh,
wherever. If I had Google for my house, I
yeah,
would
yeah.
be, it would be great, right? Google for the workshop, Google for storage, and Google for the crap that's on my desk. That would be awesome. The next best thing is to document it somewhere where I can search for it. And I can't tell you how
Yeah.
many times I do that. Like, oh yeah, I did this before. Did I put this online? And look it up like, oh yeah, that's how it works. All right.
Yeah, yeah. And then, yeah, I mean, that's like putting your brain online. I think that's like, I use Evernote for that kind of thing. And that's like what they
Mm-hmm.
talk about. It's like, or I guess it's the getting things done method too. It's like getting outside of your own head. You can't store that much stuff in your short-term RAM,
Right.
and using a notebook for that kind of thing helps. But, I think this is effectively acting as your notebook too.
Yeah, it is. And the other thing that happens, obviously, is you get feedback from people.
Yeah.
You either get
On
people
the
using
internet,
things,
people are always so kind on the internet.
right? Well, I think this kind of space that we live in is a little bit different in terms of signal to noise ratio. I think you know, there've been some cranks, but mostly it's people who are just interested in things, either have a different or better way to do it, or want to apply what you've done to their own situation. An hour before we started this morning, somebody pinged me on Twitter and said, "Hey, I saw your presentation from SuperCon last year. I'm reading your paper now. I just made a scalar network analyzer. I'm going to try to apply your algorithm."
Oh, no
Like,
way.
oh,
That's great.
well, yeah. It was like literally this morning. I was setting up here, and I'm like, oh, what
Yeah.
is this? Oh, somebody's going to use my stuff. That's great,
Yeah. It's like upping your serendipity quotient.
right?
Yeah, that's great. That's really great. And I definitely want to hear about that. Before we go on, though, what is the diode clock? Since you
Yeah.
mentioned it.
So when I was a kid, this was probably 1981, 1982. Again, it was a Radio Shack book that that my parents got me, and there were the diagrams in there. It was how computers work, or the basics of digital logic, or something like that. I don't remember the exact book, but they had these diagrams in there of like and or gates that were made with just diodes and resistors. So you know how it works. You have two diodes, and to make an and gate, either one of them can pull the output low. Right, you have a pull up, and either one of the diodes can pull. And so you see these. Sometimes you see these things in where people they don't want to spend any money on a real gate or whatever. Or you used to see them in like diode ROMs in the early days. People would make the boot ROM would be, you just need a few bytes and you make it with diodes.
Yeah.
And, as a kid, I was 10, 11. I thought, I'm going to make a computer just out of diodes. and it's a reasonable thing to think, right? Here's an and here's an or gate. And it turns out you need a couple more things to actually build a computer, right? Because first you need an inverter, which you can't just do with diodes. And you need some gain, because you start chaining just and or gates together that are made with diodes, and you don't have you have gain less than one, obviously. And so sequential logic is just out. You're never going to make a flip-flop. You can't have memory, and so you can't have a computer. And I thought about this for a long time. I'm like, there must be a way. And probably around 2002, 2001, 2002, I was doing some work with pin diode switches for I was building a Doppler radar.
Oh, cool.
And so pin diodes
this is like the I think Greg talks about that in the coffee can radar thing. It wasn't coffee can radar, right?
Yeah, no, okay. It was just a Doppler radar made with 4 or 8 antennas that you switch rapidly in succession.
Oh, cool. Okay.
To emulate a rotating antenna, and but you use pin diodes to do this RF switching, and pin diodes are, they're just one of these kind of esoteric kind of diodes you hear about that you pass a DC current through them, and then all of a sudden they have a low impedance to RF. And the interesting thing about them, you see them in amateur radio transceivers all the time, and all sorts of radio. You can switch more power than you put in. So it's really like a switch. You really can achieve amplification if you want. I thought, oh, that's it. So I'll use a pin diode to switch RF, and then I'll rectify that RF. Like, you think of a crystal radio, right? You're taking RF and you're making DC output, and I can use that to drive the next stage. And so I, was able to prototype this relatively quickly. And then I realized that you can use rectifier diodes, big slow rectifier diodes, your 1N4007s that you see, the big one. They work as really crude pin diodes. So between those, at certain frequencies, they're good. So between those and some silicon switching diodes, right, your 1N914s or 4148s or whatever, just with those two kind of diodes, you can make logic gates, any kind of logic gates. So you can make NANDs and NORs and flip-flops and everything you need to build a computer. Now, if you used real pin diodes and Schottky diodes for that were real RF components, you probably could make this go pretty fast. I wanted to make it with the kind of junk you find on, that you sweep up after a day in the lab, which are these, these commodity diodes you never think anything of, right? You see them in power supplies and wherever else, but otherwise you don't think about them. And so came up with a circuit that would do it. It took a little doing because they're very inefficient as pin diodes, and you don't get a lot of amplification. So I needed a couple of stages, but I was able to build a logic family out of them. And as an example, I built a digital clock that just uses diodes for all the counters.
That's great.
And of course, the display is LED, so that's diodes too. And the only thing that isn't diodes is, I have a time base that's not diode based because I wanted it to be relatively accurate, and the power supply, because it requires an RF power supply, to run it. So that was actually the project. Yeah, go ahead.
Yeah, but this also seems like it gets a little out of hand. So I'm just looking through
it was completely out of hand.
The instructions, which people can go and read on the hack. We'll link all the pages and stuff. Step 1: build 46 DDL01 hex NOR boards. This will include soldering over 7,000 components, so allow yourself at least a few weeks. What?
Yeah, they have an instruction section on the page, so I filled in, what you'd need to do. Yeah, it had 46 boards, and they're like 3 by 4 inches. They're not small, and they're all through-hole components. So you bend a couple thousand components and stuff them in the board, flip it over, solder it. Yeah, it was a fun summer.
Yeah, the entire summer, I'm sure. Right. So you need so many because each board is what, has a couple of NORs on it? Is that the idea?
Each board is 6. Yeah, it's a hex NOR.
Yeah. Okay.
And I went with hex because you could make a flip flop. You could make a negative edge trigger D flip flop with 6 NOR gates. And so, and depending on how you set jumpers on the board, it's 6 NOR gates, or it's a flip flop, or it's 3 RS latches.
Oh, nice. Okay.
And then you can just use the same board for different parts of the clock.
Did you do a cost comparison of what it would be to buy a hex NOR in a chip form versus a? That's a dumb question to ask. I'm sorry, that was a dumb question to ask.
If I ever wrote down how much that project cost and my wife found out about it, I'd be in trouble. So
yeah, I'll just bleep out this entire section.
Yeah. That's right.
Oh my goodness!
A lot of those parts were eBay finds, and in fact, the design. I had to tweak the design because the inductors I found inductors incredibly cheap, and I think I have the world's last supply of those particular ones because they were, they stopped making them, and so somebody had this warehouse full they were selling, and I picked them up dirt cheap, and I had to build the circuit around the inductors that I had, so I had to tweak the other components to make that work.
So I'm not sure I quite understand the how it's working here though. So you're saying, okay, so the 1N4007 is working as the pin diode. What is the frequency that you're passing through it that you then rectify?
All right. So the power supply is around 6 megahertz.
Okay.
So that's the power supply. It's not 5 volts. It's not 3.5. It's 6 megahertz, and it's plus or minus 12 volts approximately. It varies a bit. Okay. But essentially you have this big, the 6 megahertz square wave, and they're harmonics, obviously. And with the pin diode, or the 1N4007 that's standing in as a pin diode, if you apply a DC bias across it, you use an inductor, right, to apply a DC bias so that the RF doesn't get back into your DC supply. Mm-hmm. You apply a DC bias to it, it kind of shorts out that RF energy. Right. Okay. So it's a shunt. It's used in a shunt pin switch, and so if you apply DC bias from one of the inputs, that shuts off the output.
Got it.
So that's an inverter. All right. And the output at that point is RF, and you just rectify that with a couple more diodes, with some faster diodes, and then it becomes DC again, and you can use that to switch the next stage. And so
I
that's
see.
really
Okay, that's the piece I was missing. So that's because the signal then gets switched back to. So then you'd see the 6 megahertz power supply going to everything as like that's like the rail effectively. And then you're saying that
absolutely.
this, yeah, okay. Then the DC is what. So that first DC signal that gets pushed through is that.
That's
Uh,
the logic.
that's the logic.
That's
Got it.
that's the logic signal, right?
Cool. Wow. Yeah, that's weird. And then so the end of this, so looking at the picture, it's like basically just showing like a binary clock then at the end of the day, like a
It's
large
yeah,
scale.
yeah. It's just a big digital clock.
Yeah, that's great. That's great. Okay. Well,
Yeah.
that's a large. I mean, it was what was the approximate dimensions on that kind of thing?
It's about 2 foot tall.
Okay.
I think I have it somewhere. Yeah, it's about 2 feet. I built this wooden crate for it for storage, and because
Yeah.
I took it to like a maker fair, and I took it a couple places, and
Yeah.
I still have it in my office, like in the corner. And every once in a while, it's bolted. It's this big wooden crate bolted together, and I have to get the socket set out and unbolt it. And I take it out and look at it for a while, and I put it
It's like
back.
the Ark of the Covenant at the end of the
Right.
yeah, Indiana Jones. Yeah. So, well, what else? I mean, what are some of the other projects that you like talking about on your page? I mean, because you do have a couple
Yes.
here.
Yeah. So there are a couple. So one is the Tritoled. Tritoled. I made up the name. I don't know how to say it. But essentially it's a battery based LED that can run for 10 years. And so when I used to be into a lot of astrophotography, and I was constantly tripping over stuff because you work in the dark, right? And you've got a tripod, you got 3 legs, and you got 2 of your own, and inevitably they get confused, and you trip over, and you break some expensive equipment, or you hurt yourself, or both. And so I was looking for a good solution to put on the tripod legs so I could see them in the dark. And you can buy glow in the dark stuff that needs to be charged up. So and then it fades over time. The perfect thing is these tritium lights that unfortunately you can't buy in the States just as markers. Right? You can buy tritium, and what they have is they have radioactive tritium and a phosphor in there, and it glows. It's typically tritiated water in there, and the tritium's radioactive, and it makes the phosphor glow. You can buy them in compasses in the U.S. You can buy them in watch dials.
Oh, okay. So it's like the what do they call it? The glow something. I forgot what the brand name was. It used to be like the hand.
Luminox makes watches.
Okay. Yeah.
And so you can buy them in certain and in gun sites, of course, in the U.S. you can buy them in gun sites. But you can't buy just markers that and you can find them on eBay. They're illegal to import, but you can find them if you want. But I thought that's the perfect thing. What if I had an electronic one? And so you can get you put a battery and an LED together, and maybe a resistor so it's not that bright because you don't want to blind yourself at night. And you have to change the battery often, and it just doesn't make a lot of sense. So I said, well, how far can I go? With a small coin cell, lithium coin cell, like a CR2032, and an LED. And it turns out you can light it for 10 years.
Wow.
Mostly
like fully on, or not fully on, but like on
not
the whole
fully
time.
On. Yeah, on. I mean, on. You can certainly see it in at a 10-year rate. I don't think you can see it in daylight.
Okay.
But at a 1-year rate, you can. And certainly at night, you need to turn it down anyway.
Mm-hmm.
And so I had these little things that just fit. They're just a little bit bigger in diameter than the CR2032. And I found some plastic cases on eBay that they fit into. And you can build these things, and it has a little button on there. You can set the run rate, from 1 year to 10 years, and just put them anywhere. So I was walking around here today in the shop. I was digging through some of the drawers, and there's a little, green glowing light in the back. Oh yeah, there's another one. I just have them everywhere. Anywhere I need to mark something.
Yeah.
And people have written, that they make them, they put them on the corner of the sofa so they don't hit their leg at night when they go to get a glass of water or whatever.
Yeah. Yeah, because you just need like a location finding more than you need an actual lighting. You just need to know relative locations, really, of like
that's right.
hard objects.
Yeah, and that was the idea. And it turns out there's a commercial application for this. There are still film processing companies that make photographic film.
Really?
And they make them, and they get them on these big rolls, and they need to cut them up and put them in smaller packages, and they need to work completely in the dark. Obviously, it's not all automated. They have people working in there, and in some of these factories, they actually use the tritium lights that we talked about earlier, these radioactive lights. And there's this big push to kind of get rid of them because somebody has to make the tritium, and the U.S. doesn't want tritium all around the world because tritium is an important component of certain weapons.
Yeah.
And so there's a push to kind of not use these things anymore for, I don't know if the reasons are well founded or not, right? There's some irrational fear of radioactive stuff out there for sure. But in any case, if they get legislated away, they need a replacement. And so these could work.
Yeah. So what's on board these things then?
So there's actually a microprocessor on there. Okay. This is a PIC, a 12F PIC,
yeah. eight pin.
Yeah. 8 pin. And it has like incredibly low sleep current. And in fact, the thing is asleep for most of the time. When you turn it on, it configures some things, and it uses the built-in pulse width modulation circuit on there to drive the LED. And the way it works is the PWM triggers a one shot that produces a very small pulse of current. That pulse energizes an inductor. And across the inductor and kind of fly back with the inductor is the LED. Oh. So you've seen diodes on relay coils, for instance,
sure,
right, to absorb the kick when in this case it's an LED, and so you're using the kickback to drive the LED. Yeah. And it turns out to be a very efficient way to do it. So you control the amount of current and time that you energize the inductor for, and then that's how much ends up energizing the LED. And the key thing about this is, with modern LEDs, they're extremely efficient at a specific current. So you can measure the efficiency of the LED versus current. And there's one specific current. It depends on the size of the die, the LED die, and the specific physics of the LED at which they're efficient. Above that, you get what's called droop, which is one of the big factors in LED lighting. If you drive them with more and more current, they become less and less efficient. It turns out the same thing happens with very low currents. So if you just take a normal LED and use a very big resistor and a battery to try and make a dim LED that will last a long time, the LED is very inefficient at converting that electrical energy to light energy. And so what you want to do is you want to drive that LED with very short pulses of the current at which it's most efficient.
Yeah.
And overall,
it averages out. Yeah, right.
Yeah. And so if you drive them at 120 hertz or something, you don't see the blinking.
Right.
But the LED is coming on for a very short period at its most efficient current, and then turning off.
Wow.
With a very low duty cycle.
Well, how did you go about testing this? Because I'm guessing you did not test it for 20 years. So how were you?
I did not. No, I didn't test it for 20 years. I've had several that have been on for a number of years now. Yeah. I think the earliest ones I have are probably 2 years old.
That's great.
And the first model had about a year life, and I've been through a number of those, and I had to change their batteries. But it's based on the current draw versus the expected lifetime of the battery. The battery manufacturers will typically give you curves, voltage versus time for different drains, and so you can take those curves. And I actually found some software that can digitize graphs out of data sheets.
Yeah, I've seen this.
So you can actually get numbers back, and then use those numbers in calculations and just measure the characteristics of your device. So at 3.1 volts when the battery's fresh, it draws this much current. At 2.9, it draws this much, and you come up with a curve for your own device, and you can mix that with the curves from the battery manufacturers and predict the lifetime.
That's great.
And of course, it's all a guess, right? Because you don't know what the temperature is going to be, if these things are inside or outside or whatever. It's a best guess, but so far it's been pretty accurate.
That's great. I always wonder about so I used to do that a lot with like the data sheets, graphs and stuff too. I had to be usually I was just interpolating just myself, doing a straight line ruler type thing. But I was thought well, they didn't test every point here. What if there was a hidden spike between 2 points of data or something? Right. It's I'm going to find it if I find it. But graphs are only as good as the graph makers, and you just kind of
Yeah.
cross your fingers and hope for the best.
And that's what they say about data sheets, right? The typical means they saw it once in the lab.
That's right. Yeah. Yeah.
So,
Yeah. Got to be careful of those typical figures. Yeah.
right.
Yeah. That's cool. That's really cool. And so the idea then is just to have these hanging out for as long as they last, huh?
Yeah, exactly right.
Yeah, that's a great idea. That's a great idea. And so, what about the astrophotography? Have you avoided kicking any tripod stands since then?
I have.
Yeah.
Yeah, absolutely. They work.
Yeah, that's cool.
You can glue them to things. You can put a little magnet on the back and stick them on there, some Velcro, or whatever. I made one that was waterproof. I dunked it in the lake a little bit. Seemed okay. So
just like informal coated or something.
I put an O-ring in the case. The case screws off so that after your 10 years or whatever, you can change the battery. But I think these cases are cheap enough that you could just seal them with silicone, and when you need to change the battery, just crack them.
Yep. Well, that is a low and slow and long lifetime project. Let's go in the exact opposite direction at your latest thing. You've been working on an 8 gigahertz sampling oscilloscope. And I'm seeing a purple PCB, so I assume this is off-the-shelf parts and PCBs from the old Oshpark folks. Is that right?
It is. Yeah. The goal was to make it with stuff you could order from us or DigiKey.
Yeah.
I mean, that's like everything has got to be commodity parts.
Yeah.
Because
maybe not cheap though, but
it's surprisingly affordable. I think.
Really?
I think the BOM right now is under $100.
Oh, okay. Wow.
The PC board. It may go up a little bit. I'm in prototype 2 now. It needs a couple things, like the power supplies are off the board.
Okay.
Right. So if you want to run it off USB, you're going to need some switching supplies on there to get the various voltages you need. I need a beefier micro on there, with some more memory and those sort of things. So it might break $100, but it's not going to be that much more. So this initially came out of the research I did for the diode clock.
Okay.
Because I was researching diode switching circuits, and there's a whole bunch of pin diodes were one, and then I stumbled across the Schottky diodes for sampling, and I'm like, what is this? So I looked into it, and it turns out that for many years the fastest oscilloscopes used diodes to sample their input, right? Schottky diodes. You can look at. So I have on my desk here a Tektronix S4 sampling head. From 1968. It was introduced in 1968, and it achieves a bandwidth of 14.5 megahertz.
Oh, okay.
Gigahertz. Not megahertz.
Oh, 14.5 gigahertz.
Megahertz is no big deal.
Yeah,
14.5 gigahertz.
Wow.
And so you think, well, how did they do that in 1968?
Right.
And you start to look into it like, oh, it's just 6 diodes in the front end. That's it.
Really?
There's some resistors and capacitors and stuff. Yeah. And so it turns out Schottky diodes, and you can buy them today with the same characteristics, can switch in 10, 15 picoseconds.
Wow.
And the whole idea is you switch them on briefly and get a sample of the input and then turn them back off. And if you do this at the right rate, you can reconstruct the input signal.
And are you like kind of doing round robin where you like have the different diodes doing like offset from one another or what?
No, they're all doing the same sample. And so the way it works, and this is the real interesting part, is these sampling oscilloscopes use kind of a stroboscopic effect, right? If you think about, you want like an old movie, right? A silent film with wagon wheels. You'd see a movie, you see them like they look like they're rotating backwards, or look like they're stopped or whatever, because there's interference and aliasing between the frequency of the wheel turning and the 24 hertz of the camera or whatever. But you can do the same thing with waveforms. So if you and I think of an oscilloscope today, a digital oscilloscope, well, you've got this analog to digital converter on the front end, and you run it at 100 megasamples per second. And they may be interleaved, like you mentioned, but let's say they're not. Let's say you actually can run at full rate with one ADC. You sample, every nanosecond, and you jam it into a fast RAM, and then you save all these samples, and you apply your sync reconstruction or whatever you want to do, and you reconstruct the data. It turns out you don't need to do that if your signal is repetitive, which for a lot of signals, that's a good model, right? If let's say you have a sine wave, well, 1 gigahertz sine wave repeats every nanosecond, right?
Yeah.
And so you can take the first sample right after your trigger point, and then a couple waves later, you can take the second sample. As long as it's the right place from your trigger point on the waveform, it doesn't matter that you took it then or you took it at the beginning. And so then you can take the next one in a week, and you take the third, the fourth sample a month later. And as long as everything's stable, your sine wave doesn't change, frequency doesn't change, amplitude doesn't change, you can do that. You can extend that time as long as you want. They call this equivalent time sampling.
Huh.
So you can actually sample. I have in the lab here, I have a Tektronix 11801 oscilloscope. This is from 1989 or so. And in there, I have a 20 gigahertz sampling head. This 20 gigahertz bandwidth sampling head runs at 100 kilohertz. So it's only sampling at 100 kilohertz. And yet you can reconstruct signals that have 20 gigahertz components. And this is extremely powerful.
Yeah, I think I'm a little confused here still.
All right.
So I think with the stereostropic thing, strobostropic, is that right?
Yeah.
Strobostropic.
Stroboscopic.
Scopic, okay.
Scopic.
Stroboscopic. I'm going to write that down so I get that right. What I'm thinking about is thinking about sine waves like you're talking about. And I remember seeing drawings in a textbook where you have a sample, and then the next sample might be a little bit higher up, and then a little bit higher up, and a little bit higher up. And even though the signal is much faster, what you're seeing is basically a reconstructed slower sine wave. Is that kind of what you're talking about here?
Yes.
Okay.
Yes. Well, in fact, if you think of that same example where the first sample is right at the zero crossing, say, of the sine wave, and the second sample you're going to put a third of the way up or a quarter of the way up or whatever. Don't put it on that same wave. Wait a couple cycles and then put it somewhere on that. Put it at that same corresponding place on the fifth reoccurrence of that sine wave. Right.
Okay.
So you've skipped the 4 cycles in between, but now you're going to take the same sample on the same place on a sine wave, but you've just skipped a bunch of the periods.
Right. I guess the math reconstruction in my head is the hard part then. So you're doing the slower actual sampling. How do you then back calculate to know that there wasn't a bunch, much like my thing with the chart, how do you not know that there's a blip in between the two sample, data points on a chart? How do you not know that there was a huge blip between your sampling points?
So the Nyquist criteria still applies.
Mm-hmm.
Still applies if you sample at if the equivalent time sampling rate, right? Because now there are 2 sampling rates. There's the real-time sampling rate at which you're actually getting the points, and there's the equivalent time sampling rate at which, that counts how far you're moving along the repetitive waveform each time. As long as the equivalent time sample rate is greater than twice the highest frequency in the input, it's just the Nyquist criterion, you can reconstruct it exactly with sync interpolation, just like you can with normal sampling.
So then how are you able to verify this on your bench then? I mean, do you need to use your similar 20 gigahertz head unit that you're talking about?
Yeah, it's a challenge. So you can compare against a known good oscilloscope. It turns out there really aren't any known perfect oscilloscopes. There was a paper that was published by Picosecond Pulse Labs many years ago where they rounded up 9 of these sampling oscilloscopes, the fastest ones in the world, and they applied the same input to them. And they all look different. Slightly different, right? But different enough that you'd be like, well, which one's right?
Yeah.
And you're not quite sure. And to some extent, it doesn't matter, right? At those speeds, you need to get what you're getting out of the data, and you need to understand the response of the scope itself. And really, it forces you back into, if you deal with even your multimeter, right? You try to measure current, very low current with your multimeter, and then you have to kind of think about meter burden, right? How much current is the meter itself taking, right? You're trying to measure a voltage at very low current, and how much does the meter itself change the measurement? In this case, it's not necessarily changing the waveform, but it's affecting what you see. And so you have to take that into account. But yeah, I'm comparing it against the 20 gigahertz sampling head I have. You can test the bandwidth of an oscilloscope with a really fast edge.
Right.
right? So maybe you've seen this in one of the Jim Williams app notes
Yeah, he
from
loved
years
doing
ago.
that one shot kind of fast rising edge type of thing, right?
Right. And, he used an avalanche transistor. Back in the day, they would use a step recovery diode, another special diode that just had this characteristic where it would turn off very quickly. You can buy that. I found one of them at Mauser. DigiKey doesn't stock any. And so I played with that a little bit, but really want to use, I wanted to use commodity components, right? Things that may be around for a little while today. And so it turns out there are a number of things. So there's ECL gates can switch pretty quickly.
Oh, cool.
CML gates even faster. CML comparators can switch pretty quickly. And a lot of parts designed for optical networking. Obviously, if you're going to run 10 gigabits through a circuit, it needs to switch pretty quickly.
Yeah.
And
right.
so there are some limiting amplifiers or laser diode drivers that can switch in tens of picoseconds. That's plenty fast if you want to test your 100 gigahertz Regal or Siglent scope. That's more than you need. When you get down to testing an 8 gigahertz scope, that's on the order of the rise time of the scope itself. So you kind of have to correct for the fact that the edge isn't as fast as you'd like. And so you kind of get into this gray area where, what have I actually measured? How accurate is this? And to some extent, it doesn't matter, right? You just want to make sure that you're sampling fast enough so that you don't alias. You'd like to understand the bandwidth of the scope, but it becomes difficult to measure that way. The best estimate I have right now is that it has about a 48 picosecond rise time. And just to put that in perspective, if you're not used to dealing with picoseconds, which I wasn't until recently, it may not make a lot of sense. So light travels, 3 times 10 to the 8 meters per second. That's pretty fast.
Yep.
In 48 picoseconds, light travels 14.4 millimeters, which is about the width of your little finger.
That's
pretty fast.
Yeah, it's pretty fast.
Yeah, that's the rise time of the of this oscilloscope. And it turns out that the key to making that with commodity components these days is to kind of forget the special diodes that they used in the 60s. You can still make them like that, and you can still get diodes that are fast enough, but it's difficult to produce the sampling pulse that you need without the step recovery diodes that you just can't get anymore. They've kind of become unobtainium.
Right. Yeah, because they're probably not doing like custom recipes for that kind of thing. They're all switching to cheaper processes and stuff like that.
That's exactly right.
Yeah.
And so it turns out there's another architecture that came about. There was a master's thesis at UCLA in 1975 where the idea was, it was S.P. McCabe. I'm just remembering his name now, S.P. McCabe. The idea was that you could use a fast comparator to sample the waveform. And you think, well, how does that work, right? Comparators there's no time component really to it. It turns out if you build a comparator with a latch input, which is very common, they're off-the-shelf components these days, you can use that latch input as the stroboscopic input to sample your input waveform at a particular point. And the complication is that it's just a comparator. It just tells you whether the input was higher or lower than some reference.
Right.
And so you can do the same thing that they do with successive approximation ADCs, right? Where you take a voltage, use that as a reference, and see whether the input is higher or lower than the voltage.
Yep.
And then based on the results of that, you adjust the voltage and try it again. And so you can do this kind of binary search.
Yeah, it's like a binning kind of thing, but with just two bins that move around, right?
Yeah, that's exactly right. And you just do this, and so it takes you, if you want 12 bits of convert 12 bits of ADC, it takes you 12 samples to do this, but now you've come up with an estimate of what the input is. And you can do that at speed. So you can do that and get 8 gigahertz bandwidth out of it with a commodity comparator. This is an Analog Devices ADCMP 582. It's tough to say. Comparator that has an 8 gigahertz input bandwidth. In single quantities, it's less than $20.
Wow.
Not much less, but 19 something.
Right.
Right. I think in hundreds, it's $8. something like that.
What's the application for that usually? Is it usually doing like higher like RF type stuff or?
They use it in networking, to
Oh,
square
okay,
things up,
sure.
right? Receivers. They list, test equipment and the usual kind of things. But you'd find this any place you need a really fast comparison. I think when you think of normal comparators, you think, oh, maybe it's a microsecond, or really fast comparators like from the Jim William days, the LT 1016, right? That was 4 nanosecond, maybe 5 nanosecond comparator. This is 180 picoseconds. So much, much faster. They're built on silicon germanium process,
Oh,
which
okay,
is
yeah.
just amazingly fast. Um, and so, they're parts from 2019, right? I mean, this is what we have available. These are leading edge things. And,
Yeah, that's great. So what is the status of this project then? Because I was looking at a tweet from October 2nd, and it looked like you had you said an RMS error of 700 femtoseconds, but it is also showing a scatter plot that approximates the waveform, I believe, right?
yeah, that probably, I'll have to bring that up, but I think that was that's the time based calibration.
Uh huh.
So I think the error there was 700 femtoseconds. It is better than that now.
Oh,
I
great.
don't know that I have yeah. So that was just some measurement error. So it turns out there's part of this is generating the delay so that you can sample the signal at the points you want to. That's really, the first part was getting the comparator to do its job. And the second part is this time base where you need to move this sample over slightly with every repetition of the waveform. And there's a part you can buy that's used for timing, adjusting the edges on clocks. It's an ECL time delay part that's adjustable. It has 1024 steps, and you can move the steps in roughly increments of 10 picoseconds. And it might be 9, it might be 11. And you can use that to do your sampling. And then there's an analog fine tuning voltage in there that you can tune. And I've run that with a 12-bit DAC. And so theoretically, you've got a resolution of about 20 femtoseconds that you can tune this thing. Obviously, jitter's a lot bigger than that, and there's noise. And so you don't actually, you don't get anywhere near that precision, but that's the resolution that you can tune it with. And so now you've got this thing that you can tune, and you got to figure out how you can measure it. How do we measure it and then adjust this tuning voltage to get the samples exactly where we want them? And it turns out it's a delay line. And so one of the ways you can calibrate this is turn it into an oscillator. So you take the output of the delay line and feed it through an inverter and feed it back into the input. And depending on what the delay is, it oscillates at a different frequency. And so you can run this for 100 milliseconds or so, and count how many times it oscillates in 100 milliseconds, and then from that determine how long the delay is. And you can use this to calibrate, and you can get easily into the hundreds of femtoseconds of accuracy of calibrating the delay through this line.
And that's just a standard. So because it's a known transmission line kind of thing, is that the idea?
Yeah, because the line itself, it's just a trace on the printed circuit board, and because you can measure the frequency with the delay set to minimum, and then with the delay set to values above the minimum, you can just subtract off the delay from when it was at zero. Because you don't really care about the absolute delay.
Right, yeah.
You care about the relative delay. The absolute delay just moves the waveform on the screen of an oscilloscope left or right.
Yeah.
Right? That's just kind of,
moving. What's that called? Not an offset. That's
it's just an off.
Yeah. That's like from the intercept type of thing when you're moving it back and forth on the screen,
Right. Like if you change the trigger point, you get that.
Right.
You
exactly.
change the trigger, you just move the trigger point, I guess, is what you do. So you don't care about the absolute time necessarily. You care about the relative time from the trigger point.
So what are you going to use this for? I mean, just for other diode clock type things?
This is the kind of thing that you need to open up a space for other people to work on, to work on fast things, right?
Yeah.
So when I started this project, I had a 300 megahertz oscilloscope. It's actually one I bought with the winnings from that round of the Hackaday Prize.
Oh, nice.
So I had that 300. Yeah,
Paid it forward.
When I bought it, it was a 70 megahertz Regal, and you know how they upgrade, it became a 300 megahertz. And I realized within like a month of seriously working on this project that I couldn't do it. Like whoever made the fastest oscilloscope at any point in time bootstrapped it,
Right.
They didn't have faster equipment. So you got to give them a lot of credit for doing that. But I just wasn't in a position to do it. So in order to build, a really fast oscilloscope, I needed a faster one. So I bought a used 1 gigahertz tech off eBay. And that lasted about 4 months until I needed a faster one. And then I bought the 20 gigahertz one.
Right.
And
am I going to be bleeping this section out too for your wife? Is that the other one?
We probably should.
I mean, she could probably just walk in the lab and see all the boxes showing up from eBay. You bought a what?
It's a 30-year-old scope though. So, so I got it cheap, hon. It's a 30-year-old scope.
Right.
But, now I'm looking at the 50 gigahertz sampling head for it. Like, oh, can I afford it? Just drop it in, then I get 50 gigahertz. Mm-hmm. And the thing is, I couldn't have done a whole bunch of steps along the way unless I had something that went this fast.
Mm.
But now I have an 8 gigahertz scope. And, once it's in a state that people can reliably and repeatably make these themselves, then a whole bunch of people can have 8 gigahertz scopes, for $100 BOM cost. And now what can they build with that?
Right. Yep.
Right. So, you've got to build the infrastructure because, you can find one of those tech scopes maybe for $800 for the mainframe and maybe another $400 for the, so, $1,000, maybe you could have it, have one. Yeah. That's a lot of money.
Yeah, it is. Yeah.
Right. But, if I can buy one like that and use it to come up with an 8 gigahertz scope that people can get for $100, there's a whole bunch of people who might do some interesting things and want to, and be able to afford $100 of equipment to do it.
Yeah. Yeah. You just never know what's going to pop out of that. Right.
Yeah, exactly. I mean, I look at, some applications for it. So, you can, right now I'm using it to measure transmission lines, to measure PC boards. Mm-hmm. So you can measure the impedance of traces, right? You can see if those calculators you find online are lying to you or not. In many cases they are.
Oh yeah.
Right. So you can measure the impedance of traces. Are you close to 50 ohms? Are you not? Is the problem with your connector or with the trace or the pads on your footprint? And you can measure down to a 5 millimeter accuracy with this. Wow. So if you have a trace on your PC board that's 5 millimeters or longer, you can determine what the impedance is.
What does that measurement look like?
So there's this thing called time domain reflectometry. Yep. And so it's a big word. It's a very simple concept. Think about radar, right? So in the World War II radar systems, you sent out this blip of electromagnetic energy. It bounced off something.
That's right.
You counted how long it take to return, and then it tells you the distance. Well, this is the same thing, but inside a wire or inside a transmission line. Yep. So you send out a signal, in this case, just a step, right, down a wire. And when that step encounters impedance discontinuity, so you have a 50 ohm cable and somebody spliced in a piece of 75 ohm because that's what they had around. At that place where those cables are spliced, because it's going from 50 to 75 ohms, there's a reflectance there, right? There's a reflectance coefficient of 75 minus 50 over 75 plus 50, 20% comes back, right? And so if you analyze the waveform that comes back on the wire, you can say, oh, okay, there's a 20% reflection at this point in the wire. That means the impedance of that section of wire is 75 ohms. And so you can tell, because of the time it came back, exactly where that discontinuity is. And because of the amplitude of the discontinuity, whether it's 75 ohms or 60 ohms or 30 ohms or whatever, you can tell what the impedance is of that section of transmission line. And so you can use this to look at a trace on a PC board. So, you send a pulse down and look at the return, and you can see the cable, and you can see the connector, whether it's, the impedance are higher or lower than 50 ohms. You can see the trace on the PC board. You can see other components there. And so it's a way to measure these discontinuities on a transmission line. And these are the kind of things that are going to mess you up, right? When you're designing RF circuits or high speed circuits, if you have reflections at these points, well, that means that, first of all, you're going to have to deal with those reflections might come back. They might bounce around in there and cause problems, later on, or it may just prevent, signals from getting where they need to go.
Right.
So that you can, that I've got a TDR head for this. It's probably another $20 that you kind of screw onto the input here. And that has a splitter in there. It takes care of sending the signal down the wire and returning it back to the sampling head. And, you end up with a display that's calibrated. The y-axis is calibrated in ohms and the x-axis is calibrated in time. And you can say, at 20 nanoseconds down the wire, it's 50 ohms, and then it goes up to 70. And what's wrong with my PC board at that point?
Right. And this is relative as well, right? Because if you assumed it was a 50 ohm to start with, but it was actually 60, wouldn't that change? You wouldn't know you just know the magnitude change of the two things, right?
Yeah, and the way you calibrate is you put on a 50 ohm terminator.
Right. Yep.
And so it's all relative, but you can calibrate
right.
it. So
yep.
you get a good precise 50 ohm terminator and you put that on and you tune it until that's 50.
Yep.
And then everything else is relative to that.
Right.
So,
right.
If you bought the cheap eBay terminator, you may not be that accurate.
Yeah. I was lucky enough to have a VNA here, and they sent me a cal kit, which is nice too. And I was just like, wow, why do I need this? And then I was like, oh, I know why I need this.
Right.
Yeah.
They're not cheap.
Yeah. And speaking of VNAs, well, you weren't working with the VNA, but you have a paper you wrote for Hackaday, the Hackaday Journal, which I've never saw, but I saw the video where Mike interviewed about it. And so you were doing stuff with not a VNA, but a spectrum analyzer and a tracking generator. What was that kind of thing?
Yeah, so I saw the model. You had the Siglent 3.2 gigahertz.
That's right, the SVA 1032 that Shahryar reviewed.
So Regal was the first one to come out with these really cheap spectrum analyzers, and it was late 2011 or early 2012. They came out with the DSA 815, and the first time I saw it online, like within 20 minutes, I ordered one. Like I saw the thing announced, and it was like $1,500.
Yeah,
maybe.
I remember that came out. Yeah,
you couldn't get. I mean, this was cheaper like by half than the used HPs that could do the same thing.
Yep, exactly.
Right? And it goes up to 1.5 gigahertz or whatever. And I said, because I had struggled with with this for a long time doing RF. And really, I mean, once you've had one, you understand why you'd need one.
Yeah. Oh yeah. I mean, and that's the thing. I think that putting it into, this is like kind of goes back to the idea of like teaching and like having that thing in front of you, like having a measurement there and being able to modify it. You might not get, I still don't get everything about it. However, I'm developing an intuitive sense. I'm doing that mental model based on the things that my eyeballs, are passing to my brain. And like it's just, there's very few things that can replace that in my mind.
Absolutely. And I found that, I would write stuff down on paper or maybe do a simulation or whatever. And I might have got the math right, but my assumptions were wrong.
Yeah, exactly.
Like if everything were perfect, this is how it would be. But oh yeah, this isn't right.
But I bought a thing off eBay. I bought a 65 ohm load on eBay by accident.
That's right.
Or not on accident.
Yeah. and there's nothing like actually seeing it work or not work.
Yeah.
So I bought this thing, and it turns out I got one of the very early units. They improved it over time, but the unit I had, and it came with a tracking generator. Now the unit you had did vector measurements. Is that right?
That's right. Yeah.
I think that's relatively new in these.
Yeah, I think it is. And maybe you could break out what a tracking generator is versus the spectrum analyzer input.
Yeah. So the spectrum analyzer, it will just tell you how much power there is at every frequency.
Right.
That's all it does. It sweeps over frequency and tells you how much power there is.
Right.
Now, what a tracking generator does is it generates a signal that's in sync with that sweep. So when the spectrum analyzer is analyzing a little band around 100 megahertz, the tracking generator is outputting a sine wave at 100 megahertz. So what you can do is you can connect a component in between those two. So let's say you want to test a filter that's going to, you're getting some problem with FM radio stations are interfering with something else you're listening to because they're so strong and the antenna is right down the road.
I actually do have that. Sorry, I need to cut in here. I have I don't know what it is in my H6N recorder, but if people listen to one of my videos on YouTube, you can hear a radio station coming through because I live right near the Sears Tower, and that thing just cranks RF. It just cranks FM stations, and so there's like salsa music playing in the background of my videos. That's not on purpose.
Yeah.
Sorry. Anyways, go ahead. Sorry.
Yeah. So you can. So let's say you're building this FM notch filter, right? This band stop filter that's going to filter out all that stuff, so you don't have that in your videos. So you can build a filter, and then you go to test it, and you connect the tracking generator to one side of the filter, and you connect the spectrum analyzer input to the other. And as it sweeps through the 88 to 107 or 88 to 108, whatever the band is, as it sweeps through that band, you can see how much energy gets through the filter. So you can get a little plot of the response of the filter. So, does it kill all the signals, and how much are they down 50 decibels? Are they down 10 decibels? Whatever. Are there problems somewhere else? Does the signal that I want still get through? And so you can measure the response of the filter. And this combination of tracking generator and spectrum analyzer is called a scalar network analyzer. Mm-hmm. And network analyzer is just a fancy word for something that measures something with, with one or more ports, right? And you got one port and you got 2 port measurements. But what the scalar part of a scalar network analyzer means is you're just measuring the amplitude.
Right.
So you're not measuring the phase of things that go through. So there's some ambiguity when you measure certain things about what the sign, say, right, of certain things is.
Right. So like purely reactive components, you could have some problems. You don't get Smith charts, stuff like that, right?
That's exactly right. The other problem is that they're difficult to calibrate. Oh. So if you have a vector network analyzer where you're measuring the input as vectors, right, you get the amplitude and phase. If there's a phase problem somewhere in your loop, you can calibrate that out because you know what the amplitude and phase. When you take your expensive cal kit that they sent you, yep, right, and you put the through in there, and you can measure the amplitude and phase with the through, and you can do the short and the open and the load and all those things, and you can build this sophisticated model for what the test jig itself looks like.
Yep.
Right, without not even your component, just up to the measurement planes at the edge of the thing you want to test, you can build a sophisticated model for all the leakage paths and attenuations and phase shifts and all that stuff. And then when you go to apply, you put your device in there to test it, you can back all of this stuff out. So you can take what you actually measured and back out that all of the stuff that's just done to the test harness, the wiring and the connectors and all that stuff, and understand exactly what the response of just your component is. Yep. Yep. Not the cable that you used and the connectors and whatever.
As someone who buys a lot of stuff on eBay and Amazon now, you better calibrate those cables out, folks, because they're not good.
No, I have a lot of them, and I have a large bin right now of crappy cables and a very small bin of good cables.
Yeah,
and I keep them separated.
Yeah, that's good.
With a scalar network analyzer like that, it's very difficult to do this calibration. And that's what the paper was about, was coming up a way to make 2 measurements of a device and use these 2 measurements to compensate for errors inside the device. And because I bought a very early model of the spectrum analyzer, it had this horrendous leakage path from the tracking generator to the spectrum analyzer. So without anything connected externally, or even, if you put terminators on both ports, when you turned on the tracking generator, the trace went up by 20 dB. Uh-huh. So you have this, tremendous leakage inside the device somewhere. And I think they just didn't put enough shielding in there. And I think with later models, they beefed up the shielding on the board or, between sections of the board. And so the whole idea of the paper was, I've got this thing. I'm not going to open it up because it's the most expensive thing on my bench. At the time it was. I'm not going to open it up and, tack some foil in there to try to change the shielding because I don't know what I'm doing. But maybe I can do this mathematically. And it turns out you can.
That's great.
You can,
So then
you can
did you,
take two measurements, slightly different.
yeah, well,
Good.
the mathematically, did you have to push that firmware back into the device, or is this all just done externally then? Because you're just exporting data.
It's all done
Okay.
externally. Yeah. You export data. So, it has a Ethernet port on the back, like all of them do today, which is
Yeah.
awesome. And you can just grab traces and then you have that data and drag it into Python
Yep.
and do whatever you want.
Yeah, I have a friend here at my workspace who just he's been pulling a bunch of equipment that has Python APIs for everything, and that's a really nice change, you know. So Will's doing this thing where it's like instead of doing LabVIEW now, you can start to do Python scripting, and it opens up a lot of avenues.
Yeah, absolutely. I mean, it used to be all GPIB, I guess. I mean, a lot of the
that's
older
right.
equipment I have is GPIB, and I don't even know. It's some kind of weird parallel format, isn't it? I look at
It
the
is.
connector,
It's
I'm
like
it's gotta be
frames
parallel.
basically. It's
Right.
like frames.
So I haven't played with that. It's much easier just to have Ethernet.
Yeah. It's a very welcome change, I think.
Yeah.
Especially if you're building test benches and stuff like that.
Yeah, absolutely.
Have you haven't upgraded then? You've just you're really getting all the juice out of it you can, huh?
I lost an auction last night for a 22 gigahertz spectrum analyzer.
My condolences, Ted.
Yeah,
It
they're
hurts.
selling
It
them
hurts.
cheap. They're selling them cheap on eBay now. People are snapping them up.
Yeah.
So it was just a little too rich for my blood. But yeah, I'm looking to upgrade.
Yeah. I keep looking at the all the HP 8753s and all those, and those, man, I've mentioned on the show, but they don't go down. Those are flat. Yeah.
No, but they're built like tanks.
Yeah.
So the 11801, the Tektronix 20 gigahertz scope I have was built in 1989. It has 75,000 hours on it. There's a counter in there. You can look it up. Like 75,000 hours. And a lot of these things I think were on manufacturing lines.
Yeah.
So they would
right.
test, they would just be on constantly testing things. It still works fine. There's no problem. I mean, I haven't found any problem. It passes all the diagnostics, passes all the calibration tests. It's fine. I don't know how long it's going to last. One of the knobs is kind of twitchy. I have to keep tightening it up, but that's it.
Yeah. I guess how do you know that the equipment's working well enough? I mean, do you have some kind of like local calibration that you're doing? Is it just based on the cal kits you have, or what?
Yeah, so it does have internal calibration that keeps it. I mean, then you wonder, well, what if that's off?
Yeah, right. That's why you send it out every year or two to get a cal sticker, but that's pretty expensive to do.
Yeah, and I can't afford that. But it's about making a bunch of different measurements and making sure they all make sense together. So you make measurements with that. You measure some other things that you have, and you make sure that everything's consistent. Yeah. Right. So I don't really trust any of it. Right. I don't trust anything.
Yeah, that's healthy. Yeah. Right.
And the reality is I don't trust anything that I'm doing either. So you measure it 2 or 3 different ways and see if you get about the right answer. Right. And if not, why? Yeah. But you probably need to do that with, even if your stuff's all calibrated.
Right. I think that's right.
Was it the test setup? Was it the cheap eBay cable? Right.
Yeah. Right. Yeah. There's nothing more frustrating than, 20 hours into debugging and you're chasing a ghost that's actually your cable, or, right. It's not something small like, oh, you didn't plug it in, but it's more like you had something in line that you didn't think you did, or you put the wrong component on board somehow, and you're just like, oh my God. Yeah. Well, this is great. I mean, and this is just a sampling we've talked about here. Obviously, there's more on your Hackaday IO page, but you're going to be at SuperCon as well, so that's coming up in a couple weeks. Giving a talk.
Yeah. I'm giving a talk about the oscilloscope, about the sampling oscilloscope.
Oh, great. Okay, so we got a little preview here.
Yeah, so we got a little preview. There'll be a lot more details and some nice pictures of what's going on. It's kind of tough just to do it just with sound. To paint that picture of how the thing works. So I think the visuals will really make it pop.
Well, I'm looking forward to hanging out there with you, and I think that's it's a lot of fun to be there with other hardware folks. Hopefully we had a lot of good talks this year and good crowd.
Yeah, it's an amazing time. My first time was last year, and I was blown away by the thing.
Yeah, I don't know if we met. I think we met briefly last year.
We did meet briefly, yeah.
Because I think you were on my list of people to interview, and then finally got around to asking you. So I'm glad you're on the show.
Yeah, I'm glad to be here.
Yeah, cool. Well, we'll talk to you soon, and looking forward to hanging out and seeing more about your really, really fast oscilloscope.
All right, I'll see you then.
Thanks.
Thank you.
Once again, we'd like to thank our sponsor for this episode, Roden Schwartz, a leading manufacturer of value instruments designed to help you maximize your bench's performance for everyday applications. They just announced an industry first, complete solutions with all the upgrades up front for one price. Now through December 31st, 2019, save up to $10,000 on Roden Schwartz solution packages that come with fully loaded test and measurement instruments right from the start. When you invest in Roden Schwartz products, you get the highest quality engineering, plus all the bandwidth, channels, inputs, memory interfaces, and signal generation you'll ever need. Learn more about Roden Schwartz value instruments and this limited time promotion at askanengineer.us. That's askanengineer.us.